A model can look good and still be unusable because the threshold is wrong. We will sweep thresholds in Python and pick one based on cost, not guesswork. You might have a classifier that gives probabilities, but decisions are binary. You see good overall metrics, yet customers get flooded with false alarms or real issues get missed. By the end of this video, you will know how to choose a decision threshold using simple cost logic, so your model aligns with business outcomes, not just accuracy numbers. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Threshold tuning solves the gap between model scores and business decisions. A classifier's probability tells you how confident it is. But the cutoff between yes and no is where the business impact happens. Success looks like fewer costly mistakes and predictable trade-offs. People tune thresholds when false positives and false negatives carry different costs, like fraud detection, where missing fraud is worse than a false alarm. At an intuitive level, threshold tuning is just trying different cut points on the probability output. If you set the cutoff high, you make fewer positive calls and reduce false positives. If you set it low, you catch more positives, but invite more false alarms. The goal is to pick the cutoff that minimizes the harm you care about. Simple, transparent, and repeatable. We will build a tiny example with toy labels and scores, then walk through 4 progressively smarter selection strategies. You will see the default 0.5 behavior, how to maximize F1, how to directly minimize expected cost, and how to add a minimum recall requirement before picking the cheapest threshold. Keep your Python ready. Now we start with the first snippet. Now we will create toy data and inspect the default confusion trade-off. This snippet creates toy labels and scores, then shows the 0.5 confusion trade-off. This snippet builds a tiny dataset of true labels and predicted scores, so we can visualize decisions. It prints predicted labels using the common cutoff at 0.5, and then shows the confusion counts for true positives, true negatives, and false negatives at that cutoff. The core idea is to make the gap visible. You get a sense for how many errors come from each side when you treat the model like a yes or no oracle at the default threshold. If you change the cutoff logic later, those counts move in predictable ways. Next, we will compute basic precision and recall for the default threshold. This snippet computes precision and recall at the default 0.5 threshold. This snippet turns the continuous scores into binary predictions by checking if each score is at least 0.5. Then computes precision and recall. Precision is the fraction of positive predictions that were actually correct, and recall is the fraction of actual positives that were correctly detected. The important lines show how many predicted positives you made and how many actual positives you caught. If precision is high, but recall is low, you are conservative and miss many positives. If recall is high, but precision is low, you call too many things positive. Adjusting the cutoff will slide this balance. Now we will sweep thresholds to maximize F1. This snippet sweeps thresholds and selects the F1 maximizing cutoff. This snippet generates a range of candidate thresholds from low to high. Then for each cutoff, it computes precision and recall and combines them into the F1 score, which is the harmonic mean of precision and recall, and balances the two. The loop or vectorized computation finds the threshold with the highest F1 and returns that cutoff and the corresponding precision and recall. The practical point is that maximizing F1 gives you a single trade-off that treats false positives and false negatives equally in the F1 sense. So it is useful when you want a balanced decision, but not when business costs are asymmetric. Next, we will pick a threshold by direct expected cost minimization. This snippet minimizes simple expected cost to pick a business-aware threshold. This snippet defines a cost per false positive and a cost per false negative, then evaluates the total expected cost at each candidate threshold by counting the resulting false positives and false negatives and multiplying by the respective costs. The threshold that yields the lowest total cost is chosen. The key lines show how the cost weights influence the chosen cutoff. Raising the cost of false negatives pushes the threshold down, so you call more positives, while raising false positive cost moves the threshold up to be more conservative. This is the core way to align model decisions with business impact. Now we will add a minimum recall constraint before choosing the cheapest threshold. This snippet adds a minimum recall constraint before picking the cost-optimal threshold. This snippet filters candidate thresholds to those that meet a required recall level. Then, among those, it picks the threshold with the smallest expected cost, using the same cost per error idea. The important behavior is that the recall floor prevents the optimizer from choosing a super cheap threshold that simply ignores positives. Tightening the minimum recall will restrict options and often force a lower cutoff, increasing false positives, but meeting the required detection rate. Mapping this toy into production is straightforward. Replace the toy labels with a holdout set that mirrors live traffic. Replace the simple costs with documented business loss estimates per error. Run the sweep on the holdout set and record the chosen cutoff and expected cost. Repeat with time windows to keep the threshold fresh as the model or population drifts. Recap: threshold tuning chooses the probability cutoff that turns scores into decisions. Use F1 max when you want balanced precision and recall. Use cost minimization when different errors have different business values. Add constraints like minimum recall when regulations or service levels demand them. Next step: add score calibration and then retune thresholds, because better calibrated probabilities give more reliable cost and constraint estimates. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.